are now on part 2 of the SWTPC 6809 saga. This saga for me began a couple of weeks ago when I went over to Stevenage to go and pick up some test equipment that I purchased, and this was in the garage. And yeah, lo and behold, struck up a deal and this ended up in the van. I don't know how it happened, but okay, it just happened, yeah? I got this untested, and I gotta be honest, I didn't even take the case off the computer, so for all I know, it could have been empty. But luckily enough, when I got back and tested it, it pretty much worked. Apart from the terminal needing a bit of tender resuscitation and the disk drives potentially not working, everything else, well, yeah, it worked. And since that video, I've been spending quite a bit of time here and there sort of trying to get to know this machine and basically just getting it up and running and actually do something. The first port of call was having a good look at the floppy drives. It was either the likelihood that the 8-inch floppies that this came with were all corrupt because they probably hadn't been used in over 30 years, or it was the fact that the floppy drives were not functioning. So the first thing that I did was take apart the floppy drives and have a good look around and see what was going on. Annoyingly, I somehow recorded over the footage of this, but if we have a look closely in here, you'll see that it is a lot cleaner. Basically, the only things that I did in here were give it a clean the floppy heads with some cotton buds and isopropyl alcohol, and then also lubricate up all of the moving parts so it was just, you know, free and moving again. And lo and behold, after that, it was working pretty well, to the point that it probably was working beforehand anyway. So now, thankfully, everything that came with it works, and we can double check a few things now using the sbug, which is basically a ROM program that starts straight away when you turn on the computer. However, first off, let's talk about the elephant in the room. That is my name, Look Mum No Computer, and yes, this is indeed a retro computer. Ooh, dear. And there is no end of people reminding me of this fact. And the only thing that I'm going to say in reply to this is, you know, like Rolling Stones, for instance, they weren't literal stones that were rolling down a hill. The Bee Gees weren't acrobatic planes. Spice Girls aren't as spicy as, you know, the name kind of gives off. Bach, I mean, he was ahead of his time. He was thinking pretty forward. Chopin wasn't a chopping board. Elvis Presley wasn't literally a pelvis. Actually, that doesn't work. Anyway, I think I've made my point. So first off, what can we do with sbug? It came with the sbug 6809 ROM monitor, which is amazingly only about 4 pages long. Like 1, 2, 3, 4, yeah, it's about 5 pages long. And if you look through this manual, you can find out this literally talks straight to the 6809 chip, the processor chip inside of the computer. You could do lots of things that I don't really have a clue what the fudge they are. For instance, you can alter direct page registers, alter program counters, stack pointers. There's loads of different registers inside this processor. In fact, it's really quite an interesting chip. It's like the 6502 on steroids or something. If we press S, for instance, we get the stack. We can also do a memory test. This means that we'll be able to see if the memory in the computer works. However, to do the full test of the full computer, it takes 90 hours. That's more than 3 days, and I don't think I want to be sitting here for 3 days looking at this. Gosh knows what the energy bill will be like having all of these fans running. Oh no, that's the memory. Oh, one sec. I've done the wrong one. That's M. That's a different command. Don't listen to me. As you can tell, I haven't got a clue what I'm doing. So Q, which is memory test, 0000, first address, and we're not going to do the whole thing. So we're only going to check a small chunk of this, which is 000F. Every single cross that comes up is, well, when the test has gone through. We're literally only checking 16 memory addresses right now. So lo and behold, it will take a few days to do the whole computer. So now you can see how slow it is if you really want to check quite a lot of the memory on the computer. But it's going to literally take days to do this, so I'm just going to stop that right now. So initially, you can actually do quite a few things with the sbug. You could do a lot of checks, and you could just see what is going on inside the processor chip itself, and you could just basically see what is in every single memory address, basically. But you can also change what is in every single memory address, which means you can code literally on this sbug itself. So a few days ago, a kind fellow by the name of Christopher sent me this, and it has machine code on it. What is machine code, you say? Well, this is basically one step above binary. This is what the processor basically listens to. It's a string of commands that pretty much tells the processor to do certain things. And generally, all pieces of code wind down to something looking like this, albeit a heck of a lot longer than this. First off, let's try and put this string of numbers into the computer and see what happens. First off, we type in M, which is the command for sbug to let us alter the memory inside the computer. boom. And then we type in 0000, which is, like I said earlier, the first memory address. It's currently set to 3. What we need to type in is BD, which doesn't actually look like a number. This is actually hexadecimal code. Hold up 1 second, Sam. What the heck is hexadecimal code? Well, if you're a coder, it's likely you'll know what the fudge hexadecimal code is. And also, it is equally likely that the whole of this video will annoy you quite a bit. But for the other 98% of people that don't really have a fudging clue, I'm going to do what I do best, and that is slightly incorrectly try to describe something. So basically, computers talk in 0 and 1. They count to 1, 2. That's like 2 different numbers basically there. That's what they count in because it's easy for a computer to do that. Having loads of things that just switch on and off is a lot cheaper than having loads of things that sort of have a complicated function accounting to 1 to 10, for instance. The only reason we count from 1 to 10 is because we've got 10 fleshy stumps on the end of our fleshy rods. First off, we'll start with binary. Likely you'll know what the fudge is going on. But 1 bit is basically 1 number, and it's got either a 0, which is a off, and a 1, which is an on. So that means you've got 2 outputs. 2 bits, you've got, 2 numbers. So you can have like 1, 1. And that means you can either have like 0, 1, 1, 1, 1, 0, 0, 0. That means you've got 4 outputs. Blah-de-blah-de-blah. And then we skip straight over to 4 bits. That's right here. You've got 16 possible outcomes of this. Like you've got 0, 0, 0, 0, 0, 0, 0, 1, and so on. So wouldn't it be great if we could count in these sort of numbers instead of decimal numbers? Well, that's when hexadecimal comes in. Hexadecimal is, well, hexa is 6, decimal is, 10, so 16. In order to count to 16 in a decimal number, you need to use up 2 characters. What if instead we made up a bunch of numbers after 9 that sort of counted up to 16? So in essence, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which actually counts to 10. Imagine 9 is the 10th number, and then it goes A, B, C, D, E, F. So in order to count up 4 bits, all you need is 16 numbers, 0 to F. So that is the hexadecimal numbers. So if you needed 8 bits, well, all you need is 2 of the hexadecimal numbers. So basically it goes from 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, right up to 0F. And then after 0F, it, like any other number, it goes 1, 0, and then goes, and that counts up, and it goes to 1F, and then you keep on doing this right up to when you get to FF. And if you have 8 bits, it has 255 different outcomes. And if you count up to FF in this respect, well, you end up getting 255 numbers. Ooh, very nice. So hopefully, with this in mind, when you see me typing in letters and saying numbers, well, you'll see that I'm talking about hexadecimal code. Right, let's carry on typing this in. FD, B3, 8E, 00, 0C. It's typed in. We need to press Control P, which is the program to set the page counter. Type 0000. Takes it back to the start. And now if we press G, which is execute, in a way, it should start doing its thing. Yeah, it did it. It did it. Oh my God. That is a program. How cool is that? So after being quite surprised by that string of numbers in machine code, I figured I should ask him what the fudge was going on. I started by asking Christopher if they directly coded this in machine code or if they used assembler language to actually build it and then compile it down into machine code. The answer that Christopher gave was a little bit of a mixture of both. However, he did send me a copy of the assembler code that he used to put this together. So this right here is the assembly code that was used. It starts here and it ends here. It's very simple. It is basically maximum, like 7 lines long. It basically tells it to display some characters and then say, just keep on printing those characters in a roundabout way. But Christopher also kindly sent me the halfway part in between the assembly code and the machine code, which is called a list or something. So you'll start recognizing this part as the machine code from earlier that we typed into the machine. And you'll see over here, this is what was on the assembler code. These bits right here, as far as I know, are called opcodes, I think. And there are lists of these for the 6809 processor. And these correlate to certain hexadecimal hex codes that you type in. So I decided to have a look through the 6809 machine code manual, and most of it went over my head. But I managed to find the opcodes that were on this. And here they are right here. So the top two are assembly language still, and then you start going down into things that are for the 6809 processor. These are the opcodes in there. The LDX is load to register, JSR is jump to subroutine, BRA is branch always. I guess that's the one that just says keep on printing. The FCC is what I think it tells it to start listening to the next few bits of machine code as being characters to write on a screen, and that's where this big bunch of numbers come in, and they are called ASCII characters, ASCII, and this is a table of ASCII characters and the hex code that they are attributed to. As you can see here, J is 6A, uppercase is 4A, J, so L is uppercase, which is 4C, and look, mum, no computer, has a capital L in it, and if you look over here, well, there's that 4C right here. That 4C directly correlates to the L in look, mum, no computer. As you can see, that works as well, because 6F, after that, there's two of those, and that should be lowercase o, L-O-O. So 6F over here is, 6F, and that's O. Ooh. So after all of this, the code that Christopher sent sort of started to kind of make sense. Seems that these hexadecimal numbers in the machine code correlate to different commands inside the 6809 processor. And yeah, I know this is probably extremely vague to the people who knows what the fudge is going on, but you're talking to somebody who hasn't really got much coding experience. The first computer that I ever really got to know was a Windows 95 computer, and there was no coding lessons when I was at school and stuff, and I didn't pursue coding in further education and stuff, so I'm not really up to date with coding. It's not my thing. I have a vague grasp on C++ to get Arduinos ticking, but that's about as far as it goes for me. And I would love to sit down and learn this kind of stuff, but even in the 80s, it didn't go as far down as machine code. In fact, there was a program, the next step up, which is what was used here, called assembly language, and that's what's used on these computers right here. So most people didn't directly code to machine code. Having the machine code there in this sort of system is there to debug and also quickly load things like this and things from 1970s magazines. You know, you just do, if you ever remember, just typing a bunch of numbers into a computer. That's sort of this thing. So in order to use this computer further and use stuff like assembly language, we sort of need to load an operating system, and that's where we sort of got stuck in the last video. I'm going to quickly reset this. It's going to start at the bottom right now. So looking through the floppy disk that came with this, it turns out there were quite a few copies of Flex, the operating system for the SWTPC. But it turns out two of them, these two right here, were partially corrupt. That means that both of them worked in some sort of way but didn't work in another sort of way. It's down to the fact that they're old floppy disks, and yeah, they probably lost a lot of their magnetism, and you know, a lot of the data on there is sort of lost and mangled up for good. So first off, if we load this one into the floppy drive, this is disk drive number 0, D on disk bug, and it says can't read IPL, and that's the problem we had last time. But if we load this one, we pop this one in, ooh, shut that down and press D, well, it takes a little moment to load, but it tells us to type in a date. So let's type in a date. Okay, here we go. Typing in a date, and now see what happens. Okay, this is good news so far. We're sort of getting there. We're sort of getting there. Ooh, come on, do your thing. Please work. But now it says this, disk file read error. And this is what made me initially think that the disk drive probably wasn't working. So that's why I took them apart and sorted them out and gave them a good clean, just to make sure that it wasn't them, and it definitely was the disks. Now let's load from this disk drive again. So we're back here again, however, we don't go any further. We take this operating system out and we put this operating system in. Oh, here we go. And now we press enter. And now Flex has decided to load. And funnily enough, this is not the only thing that one of these floppy disks work in one respect and the other one works in another respect. So what I needed to do was make a fully working operating system out of these two half-working floppy disks. So first off, I typed in new disk, and this lets me format a floppy disk. However, this function only works with the first floppy drive, so I've got to swap that over again. One sec, I'm just going to swap it over. Put in a new floppy disk into disk drive number 1, which is this one. I think I need to set the disk drive, which is number 1, so now press enter. Are you sure? Yeah, of course I'm sure. Yes. No, it's not extended. I'm going to write Sam. I'm going to write volume number 1. This takes about 5 minutes, so I'll see you in a second. whilst this new disk is formatting, basically what I did was I sort of worked out what files were corrupt on each of the floppy disks and copied vice versa onto this until I had a fully working operating system all on one disk. And that is what's right here. And what we're going to do right now, after this floppy drive has finished formatting it, is copying this disk over to, you know, make a copy, because I've only got one right now. The thing is the manual is pretty easy to get your head around. Like, I've managed to get this far with the manual alone, and this is creating new system diskettes right here. This is just after the page about formatting a disk. And the cool thing is if the disk that is formatted has a bad sector, what it'll do is it'll just make sure that it knows that there is a bad bit in the floppy disk, and it will just, it will format it accordingly. But you can make a new disk by literally copying all of the files over to a new disk. All you need to do is type in copy from drive 0 to drive 1, and then you type in the files that you want to copy. However, if you want to copy just a whole floppy disk, all you need to do is type copy 0 to 1, which copies drive 0 to drive 1. So I've now got the floppy disk in that I want to copy, so I just go copy from drive 0 to drive 1. And this takes about 5 minutes. Let's do this. So this is trying to boot it from the operating system disk that I've just put together. Oh, type in the date again. And there we go. As you can see, no need to change a floppy disk, and it's boom, it's there. So as you can see, it's doing its thing, and I haven't really figured out what the heck to do any further than this. I guess the next thing that needs to be done is figuring out what to do with this, because I wasn't expecting on getting this. I'm not really like super up on retro computers and stuff unless there is something that is musically orientated that could be done with it. The funny thing is, if you haven't seen already the YouTube video by Stack Smashing of getting a Game Boy to mine Bitcoin, I reckon this probably would work quite well, because Game Boy is on assembly language as well as this, so you never know, it might be quite simple to get this to mine Bitcoin like an absolute boss. But for me, it is absolutely imperative that we need to make this musical. So the surprising thing is there are a number of ways that this can be done, that we can make music using the SWTPC 6809. In fact, there is a video that was put up a couple of months ago by somebody called Robin Grosset, who was exploring an old sound card that was actually built for the SWTPC 6800. And he got some PCBs from files that were made by Corsham Technologies, who makes a load of aftermarket supplies for the SWTPC. Yeah, I know, that's mad, right? There are people out there that are making new parts for these machines, which is incredible. Robin managed to get sine waves out of this sound card, as well as some speech coming from it. You should go and check the video out over there. But for me, I think the functionality of this machine will shine doing it a slightly different way. I've mainly taken this apart to sort of give it a bit of a clean, because it is pretty damn skanky, and I figured the floppy drive's now clean, I may as well do it to this one as well, but I'll do that after. But yeah, I wanted to show you what connectivity that this thing has. These ones at the top have got different serial lines, different baud rates of stuff that you can plug into these, and these are all the parallel ones. As you can see, it's got a chunk of connectivity, and it's also got bipolar power supply, plus and minus 16 volts, which is actually perfect for analog synthesizers. Ooh. So it has enough connectivity to legitimately be able to talk directly to analog synthesizer circuit boards and stuff via a few digital latches and 8-bit old school analog to digital converters. This thing can do 16 bits, but what's the point when 8-bit voltages are far more than enough to talk adequately to analog synthesizers? So the end goal with this is actually to reimagine and build an add-on synthesizer kind of expansion set that goes with this machine. Sort of imagine that you're stuck stuck in 1983, 1984 and using the similar technology, so no Arduinos, this, that and the other, and it's perfectly possible to basically build basically a box on top that is pretty much basically a groove box that connects to this. It'll have a drum machine and it will have a couple of synthesizers inside of it that will be directly sequenced by hopefully a program that is sitting on an EEPROM on the actual main board via a live updating character screen over on the terminal, because that is more than possible for this terminal and this technology. With a few other bells and whistles, I think this might actually be pretty cool. So in essence, it will be a modular synthesizer sound card built into it with basically the terminal acting sort of like a 8-bit BeatStep Pro. The hardware and the peripheral side of things are relatively straightforward, and I can pretty much do that and I can figure it all out and it'll be a nice, easy project. However, the coding and all of that jiff-jaff is way beyond me. I would love to sit down and figure that stuff out, but there's sometimes you just got to realize that maybe you just haven't got the brain cut out for something like that. So, you know, I'm not the coder kind of fellow. I'm going to try my darn hardest to get my head around it all. I've been reading up on machine code and assembly this last week, and it's been slightly over my head, but it's sort of sticking. So, you know, maybe in a couple of months. We'll see. So the next update on this machine probably won't be for a couple of months. That's because, yeah, there's a lot of stuff to figure out and work out, but I have a feeling that this could make a pretty good musical machine. It's just going to take a little bit of the old noggin. So yeah, that is the update on the SWTPC being sort of figured out and restored by a complete and utter computer illiterate. Yeah. In other news, the latest modular live stream megamix has just been put up on Patreon. I've nearly got enough of them to actually make a vinyl, but up until that point they're all downloadable over on my Patreon, which needless to say supports all of these projects. So I'm going to play out with like a minute snippet of that megamix, and you can download that and loads of other ones over on my Patreon. So if you're interested in supporting this kind of stuff, go and check it out. Anyway, I've been Look Mum No Computer. If you like what you see, don't forget to subscribe and don't be scared to try it.